Today in this video we are going to discuss about one-sided PN junction. So what do you mean by one-sided PN junction? So in a normal PN junction we said it's a bulk material, semiconducting material, and then you doped one side heavily with some donor impurity concentration, and then we said this is N region, and the accepted impurity concentration is doped with the to the other side, and we got the P region. So combined, this thing is known as a PN junction. This is what we got. So uniformly doped concentrations, you can see Na. This whole region is uniformly doped with the accepted impurity concentration Na, and this part is doped with the donor impurity concentration. As a result, we got the PN junction, right? Now, in a one-sided PN junction, what we are going to do is one side of the PN junction material will be heavily doped as compared to the other. For example, in this case, if P region is heavily doped as compared to the N region, then we can say that Na, that is the doping profile of the P side, or the accepted impurity concentration, is much larger than the donor impurity concentration Nd. So mathematically or symbolically we will say this way: Na is much larger than Nd, right? And this case is known as a P plus N one-sided junction. We will name it as P plus N. That means P region is heavily doped. You got the positive plus sign over here. That has nothing to do with any charge carrier or something. This means P region is heavily doped, right? So P plus N one-sided junction. Similarly, if N region is heavily doped, this region is heavily doped, or you can say that Nd is much larger than Nd is much larger than Na, then we will call it as N plus P, or a Pn plus one-sided PN junction, right? So this is what we mean from one-sided PN junction. But here we will see what are the variables. What happens to the variables if when we take a P plus N junction or a N plus P junction. Let us start with a P plus N junction, right, where we got Na, the accepted impurity concentration is much larger than the donor impurity concentration. What will happen to the abrupt boundaries that we have already discussed? Suppose the abrupt boundary here we said where we got the space charge region, the positive space charge region is extended to certain value. We said suppose this is xn plus xn we considered, and the abrupt boundary in the P region of the space charge we call it as minus xp. In symbols we wrote it this way, and we have already determined these values xn and xp for a thermal equilibrium condition, for a reverse applied bias condition, right? So now we are going to see in the reverse applied bias condition what will happen to the xn value, xp value, w, that is the space charge width, which we said xn plus xp, and to the junction capacitance value, okay, for a one-sided PN junction. This is what we are going to see in this particular video, okay. So let me just write the values of xn, xp, and w, c dash, all these, okay, one by one for reverse applied bias condition in a PN junction. In normal PN junction, okay, uniformly doped, both regions, P region and N region is uniformly doped. But what will happen to, and then we will extend it to one-sided PN junction, okay. So now the value of xn and xp that was already determined for a reverse applied bias. I am just writing those values. It is 2 epsilon s, and for reverse applied bias you have VVI plus VR. In thermal equilibrium you will have only VVI value. We have already discussed in one video, you can see that, okay. And this divided by E, and then Na by Nd, okay, and then 1 by Na plus Nd to the power 1 by 2. This is the value for xn. Xn is what? The abrupt boundary of the space charge region in the N region of the PN junction, right? Now here, if I write it for a P plus N junction, P plus N junction, where we said that the Na value is much larger than Nd, then what will happen to the xn value? Let us see. Okay, so now you can see if I will take Na is much larger than Nd, here in this term you can see Nd can be ignored as compared to Na. Then you got a Na over here, Na and Na will be cancelled then. So we the rest whatever is there we can write. So the Xn value here, the abrupt boundary in the n region for a p plus n one-sided junction now can be written as 2 epsilon s Vbi built-in potential barrier plus Vr the reverse applied potential divided by E the electronic charge, the electronic charge, and Nd to the power 1 by 2. So this is what we can write. Similarly, for xp value we have already determined for the reverse bias potential. We can write 2 epsilon s Vbi plus Vr. Easy to remember, this is just opposite to this whatever we got for xn. So here Na by Nd, you will write Nd by Na here in the expression. Okay, and then Na plus Nd as it is there in both the cases to the power 1 by 2. To the power 1 by 2. Now you take the same thing, Na is much larger than Nd, you consider here. So you can say Nd can be ignored. Now you got Nd divided by Na into Na square you got, right? Na into Na squared. So if I will rewrite the value for xp for a p plus n junction, p plus n junction, if I will p plus n one-sided junction, if I write what is xp, we got xp is equal to 2 epsilon s Vbi plus Vr divided by E, and then we have this Nd as it is. We ignored this Nd here, okay, it's very small, so we got this Nd divided by Na square, right, to the power 1 by 2. So to the power 1 by 2. Okay, so now you have the xn value and xp value for the p plus n junction. P plus n one-sided junction, we have the values for xn and xp, right? Now if you want to write what is the space charge width, W is equal to actually the magnitude of xn and xp, because that gives you what, the this is the metallurgical junction, x is equal to 0, you got x is equal to xn, right, and you got x is equal to minus xp, right? So this whole thing was the space charge width. So I will just add this value which is the magnitude of xp and this value which is the magnitude of xn to get the W value, right? So simple here. Now if you see the values over here that we obtained for xn and xp, okay, so for xn and xp only you can see you got a value of Na square. We know that Na is much larger than Nd in what, in the one-sided junction, in a p plus n junction, right, in a p plus n junction, right? So if we'll take this Na is very large as compared to Nd, right, then what will happen, this value will be very small, right, very small. And what was the xn value? I erased it. Xn is equal to 2 epsilon s Vbi plus Vr divided by E, and then we had Na by Nd here, and then we had 1 by Na plus Nd. So I ignored Nd, so Nd got cancelled, and then we did cancelled Na and Na, so 1 by Nd was only there. So we had, this is Nd, End, right? Now if you see, compare this xp value and this xn value, xp and xn value, right? So you can see you got Na square and Nd is already very small. So this value actually Na square is large enough. So xp will be very small. So we can say xp is actually much smaller because Nd is small here. There is no Na value. So Nd is very small. That makes xn much larger. So you can write xp is much less than xn. Xn is bigger value. This is a bigger value. This is the small value, right? So if I write W is equal to xn plus xp, okay, I can ignore this xp as compared to xn. So we can write this is nearly equal to xn, right? Nearly equal to xn. This can also be verified. You just remember this value. Xn is equal to 2 epsilon s Vbi plus Vr END. Now if you will substitute in the condition of Na much larger than Nd, in the space charge width expression that we have already determined for the reverse applied bias, then also we can verify it. Okay, how? Okay, let me just rewrite the W value, the space charge width, which we had obtained 2 epsilon s Vbi plus Vr divided by E, and then we had Na plus Nd divided by Na-Nd. This was the expression that we determined. We had determined for W to the power 1 by 2. Now the same thing, what the condition was, Na is much larger than Nd, right? So here, if I will consider, I will ignore this Nd. You can see Na is there, Na will be cancelled. So you got this, okay? So that gives us 2 epsilon s Vbi plus Vr divided by E and End, right? This to the power 1 by 2, right? Which is exactly your xn, right? So xn is equal to 2 epsilon s, sorry, there is a to the power 1 by 2 term here. I forgot 1 by 2 here. Okay, so you got this W is nothing but actually your xn, right? So in one-sided Pn junction, for example, a P plus N junction, the space charge width will be this. Space charge width is nearly equal or is equal to xn, and xp is very small, and you can ignore the value of xp. Okay, because you got a Na square value here, which actually makes the value of xp very less. Okay, so we are done with the xn xp, the abrupt boundaries in a one-sided Pn junction. And then we showed that the space charge width is almost equal to the space charge width of what? The abrupt boundary value xn. Space charge width W is equal to xn. It is what we showed. Now the next important factor that we need to consider in a one-sided Pn junction in reverse applied bias case is the junction capacitance. So let us see what is junction capacitance. If you remember, the junction capacitance for reverse applied bias in a Pn junction we have already determined, and the value is this is E epsilon s Na Nd, right, divided by, there is a 2, and then we have Vbi plus Vr, and then Na plus Nd. This is what we have already derived. Okay, Na plus Nd to the power 1 by 2 will be there. Right, this is what we have already derived. This is the value of C dash. Okay, so now in this again the same thing for P plus N. If I will take Na is much larger than Nd here, Nd can be ignored, and you got this Na. So Na and Na will be cancelled. So we can rewrite that the junction capacitance is E epsilon s Nd divided by twice of Vbi plus Vr, okay, to the power 1 by 2. This is what we got. Okay, you can see here, the junction capacitance for P plus N. E is constant, epsilon s constant, Nd constant, and 2 constant. Vbi is also constant. The variable here is Vr, right? And here C dash. So the you got the dependent parameter. If I consider this to be C dash, and the independent parameter is considered to be Vr. So in any experiment, suppose you are varying the reverse applied bias, then you are studying the C dash, and then you can plot a graph. And what should be the nature of the graph? You can see that C dash must be proportional to Vbi plus Vr to the power minus 1 by 2 here. So this should be the nature. Junction capacitance. Okay. So for normal Pn junction or a one-sided Pn junction, the relationship is this. So you must be aware of all these variables: E, epsilon s, Nd, doping profile, semiconductor permittivity, all these values, right? If you want to further analyze it, we can do it this way. Suppose I will square both the sides for C dash square expression. For the C dash square expression, that is this one. Okay, so let us take C dash square then what we will write, E epsilon S N D is there, and then we got this is 2 times VBI plus VR, right? Just squaring both the side, you have 1 by 2 into 2, so 1. So C dash square is equal to this, right? So here, if I will take the reciprocal of both the sides like this, 1 by C dash square if I will make, then what we got, 2 times VBI plus VR divided by, this is E epsilon S ND, right? Okay, this is what we got. Fine. Now, if you will just compare this to the straight line equation, this is a linear equation. You can see that if I will take this whole thing as y, this can be written as y is equal to mx plus c format to give you the to give you a straight line or linear equation. You can see, so where y is 1 by c dash square, your m is nothing but 2 divided by E epsilon S and D, right? And the variable is VR, right? So you got this whole thing and multiplied with VR. VR is the variable, your variable, that is the independent variable, plus you have the 2VBI divided by E epsilon S and D. This thing represents the constant here, the intercept, y intercept, you can see, right? So now if you want to plot it this way, like plot it what way? If you want to plot a graph between the reverse applied bias here, okay, this is your x, okay, the independent variable, and the dependent variable suppose we took as 1 by c dash square, then a straight line like this can be obtained, right? Whose slope will be what? The slope will be, you can see the slope is what? This 2 divided by E epsilon S and D. So sometime they will give you numericals where the slope will be given and they may ask you to find out some unknown. So this value is nothing but your minus VVI, right? This is the built-in potential barrier here. If you will extrapolate it, right? The slope or the gradient we said is equal to this value 2 divided by E epsilon S and D, right? That's the slope, and this value is the intercept, that is this value here, the y-intercept we got. This is the y-axis, y-intercept, that gives you 2 VVI divided by E epsilon S and D, right? So this is all about the one-sided junction. The same thing can now be written for N plus P, where the N region is heavily doped as compared to the P region, or you can say the impurity concentration, donor impurity concentration ND is much larger than Na, and you repeat the same thing to find out the space charge width, to know what is Xn and Xp, or to know the junction capacitance and the relationship between the junction capacitance and the reverse applied voltage. So that way you can exactly the same way you can proceed. So this is all about one-sided junction in this video. We will come with another topic in the next video. Thank you for watching.